Hello everyone, this is Nitish Deshpande, and today I will present my work on the topic Non-Uniform True Time Delay Precoding in Wideband MISO Systems. This talk is for the 2022 Asilomar Conference on Signal System and Computers. This project is in collaboration with Dr. Castellanos and Professor Robert Heath at NC State University. I will start by discussing the motivation and background for this work. Let us first discuss the fundamental limitation of phased arrays. A phased array is a popular architecture in millimeter wave systems where an RF chain is connected to multiple antennas through phase shifters. A phase shifter can modify only the phase and not the magnitude of the signal. Let us consider a scenario where we want to scale the aperture by increasing the number of antennas. The issue with having a bigger aperture is that there is array intersymbol interference, also known as the beam squint effect in frequency domain. To reduce the intersymbol interference, it is required to increase the symbol duration. However, this will reduce the bandwidth and hence the data rate. This trade-off is known as the aperture bandwidth trade-off for phased arrays, which was proved in our recent work. The other popular architecture is the fully digital spacetime architecture, which can be used to mitigate the array intersymbol interference by having multiple delays and waits at each antenna. This architecture is based on the finite impulse response precoder. With increasing the number of antennas, there is increase in the data rate. However, since it's a fully digital architecture, there is also increase in the number of RF chain components like data converters and amplifiers. This leads to increase in the overall power consumption and thus reduces the system energy efficiency. So even this architecture is not suitable for very large arrays. We need to find a middle ground between the phased arrays and the fully digital architecture. The true time delay beamforming architecture has evolved as a popular solution because a single RF chain is connected to multiple antennas through delays. These delays can create frequency-dependent phase shift, which can be used to mitigate the beam squint effect by, by having a correct beam phase over the entire bandwidth. Recent advances in circuit technology have made true time delay more practical by reducing the power consumption. There are several hardware implementations of true time delay like switched capacitor array, all-pass filter, photonic or optical beamforming methods, and Rotman lens. I will now discuss the prior work on true time delay precoding. Most of the prior work focuses on beamforming only for a single line of sight path in the far field. The delay design for this setup is very simple because it is based on the uniformly spaced delays. In practice, there can be multiple non-line of sight components or spherical wave propagation effect in the near field. The delay design for this setup is complicated because of the non-uniformly spaced delays. Hence, there is need to develop proper algorithms to design the delays in true time delay architectures to handle complicated propagation environment. I will now discuss the system model for our work. We consider a multiple input single output system and formulate it in the time domain. Assume there are multiple antennas at the transmitter, with each antenna having a precoder response of length Lg. The channel response is denoted by the vector Hi at the ith antenna. This response has length Lh. We model the channel in the baseband domain as the geometric L path channel where each path has a gain and a delay. The delay term appears in the low pass filter as well as the phase. The low pass filter can be either a sinc or a raised cosine function. The received signal can be expressed as the convolution of the effective channel response and the signal with additive Gaussian noise. The effective channel response is the convolution of the channel response and the precoder. We consider the discretized version of the received signal and denote the sampled effective channel response in this form. We express this in matrix form by using the Toeplitz matrix notation. The sampled effective channel response has the length LH plus LG minus 1 because it is convolution of the channel response of length LH and precoder of length LG. To express Qn, we rewrite this by expressing the matrix H bar as concatenation of the channel matrices for all antennas and the precoder G bar, which is concatenation of all precoders for all antennas. And now discuss the problem formulation. The total mutual information objective is given as the sum of mutual information over k subcarriers, and the signal to noise ratio is p by sigma square. Here, note that we do not assume an explicit subcarrier allocation, power allocation, because the true time delay can only apply a delay at each antenna and does not change the magnitude for each frequency. This expression is complicated because of the logarithmic term. Hence, we consider a simplified expression, which is the upper bound on total mutual information using Jensen's inequality. We can rewrite the term inside the logarithm in frequency domain using Parseval's theorem. So the final objective is the upper bound on mutual information, and this is easy because there is the standard quadratic form inside the logarithm. We now discuss the constraints on the true time delay precoding problem. The true time delay precoder should satisfy this expression, which is in terms of the pulse shaping filter and the phase. Hence, the problem P1 is the maximization of this quadratic function under the constraints of unit norm power constraint and the true time delay precoding constraint. Here, we need to design the delays Ti at each antenna. This problem is difficult to solve directly because of the second constraint of true time delay. Hence, we develop an approximate problem formulation. It is based on the following two observations. The first observation is that the channel response is sparse because it is sum of L channel paths based on the pulse shaping filter, which is a sinc function. It is sparse because it has few non-zero dominant values. The second observation is that the true time delay precoder response is also sparse because that too is based on the pulse shaping filter. Hence, the convolution of the channel and the precoder, that is the effective channel response, is also expected to be sparse. The approximate problem is given as follows. Instead of having the second constraint, we consider the modified objective function where we have a regularizer term, which is the L0 norm of the effective channel. This means we are restricting the number of non-zero elements in the effective channel. The next question is how to solve problem P2 and compute the delay at each antenna from the precoder response. And now discuss the optimization algorithm. To solve P2, we use the iteratively repeated quadratic maximization technique, which is based on the minorization maximization algorithm, that is to optimize a sequence of objective functions. The objective function is an approximation. At kth iteration, the approximate objective function depends on the weight wk, which in turn depends on the precoder response and the channel response at the previous iteration. Once we have the precoder, we need to compute the delay from the precoder response. To do this, let's consider the following. The precoder response is of this form, and we need to map it to the true time delay response, which corresponds to a sync filter. To map to the true time delay response, we align the dominant tab, which provides the integer delay, that is the integer multiple of the symbol duration. The second step is to match the phase of the dominant tab. By matching the phase, we get the fractional delay, and the overall delay is given by this expression. Hence, using this four-step procedure, we compute the delay at each antenna for every iteration and then consider the best TTD and consider the best delay design which maximizes the objective function. I will now discuss some simulation results. We plot the average mutual information as a function of the number of antennas for the phased array architecture and the true time delay architecture. For true time delay, we consider the baseline method of time reversal precoding. From this plot, we observe that our proposed method based on the IRQM approach performs better than the time reversal precoding. The second observation is that with increasing the number of antennas, there is a drop in the performance of the phased array because of the beam squint effect that occurs at higher number of antennas. Now, to explain why our proposed approach performs better than time reversal, we demonstrate the temporal focusing effect and its comparison with the time reversal precoding. Since our algorithm is iterative, we plot the magnitude response of the effective channel and the precoder at every iteration. Here we observe that as the number of iteration increases, the response for the effective channel becomes sparse. Comparing this with the time reversal precoding, we see that the for the effective channel in for time reversal precoding, the dominant tap is always the center tap, whereas for our approach, the dominant tap can be any tap offset from the center. Hence, our work generalizes the temporal focusing property of time reversal. The second observation in this plot is that by sparsifying the effective channel response, we are also sparsifying the precoder, which makes it easy to compute the delay from the precoder response. The conclusion of this work is that we have introduced the sparsity inducing norm in the true time delay optimization to exploit the idea of temporal focusing. We developed the algorithm based on minorization maximization technique to obtain a sparse solution. This technique generalizes the temporal focusing property of the time reversal precoding. For future work, we propose to extend this to the multi-user MISO setup and study the spatial focusing property. Another future direction is to incorporate circuit aspects of MIMO, include the intrinsic and extrinsic noise at the receiver, and model mutual coupling at the array. Thank you.